Okay, so I'm going to bring you in a different journey. I mean, because we're going to go wide, very big, old scale, universe scale. And to do that, we basically need a new tool, which we call radio astronomy, and I explain what it is. And more precisely, it's radio interferometry computing. And what you see here is a relatively recent picture of the center of our Milky Way that you can see at radio waves. And that tells us very much things differently than we learned before on our universe. We can see magnetic field, we can see star formation bubbles, and a lot of physical processes that were not accessible before. So, okay, there's been some character change, but anyway, so what I'm going to talk about is about this radio astronomy and how we are working with CSES and computer scientists to go into our better understanding of our universe. And we do that by improving the processing of our data, which allows us to go and to learn more about, for example, solar science and epoch of ionization or cosmology. And we do also a lot of simulations because universe is quite complex and we need to learn more from our simulations, and those simulations are run on big computers. As you're probably not much aware of our domain, so let's give you a little introduction here. As human, you're basically very familiar with photons in the optical domain, but you have not much clue about radio waves. Our atmosphere is blocking quite a bit of the signal coming from the universe. There's an optical window, and you all see stars and possibly one galaxy in the sky with your eyes, but basically at radio you know nothing. Radio window is fully open here, basically from 1 millimeter wavelengths to 10 meter wavelengths. Otherwise, you have to go to the moon or in space. But of course, just because of optics, you are very much limited in radio waves. Why? Because the image resolution you can get from radio waves is very poor. There's the array formula that you see on the top left, top right, sorry, give you the resolution in arcsecond of a signal with a wavelength lambda and a diameter of your telescope d. So typically, if you want to compare a radio telescope to an optical telescope, where you have a factor of 10,000. So basically, the biggest telescope on Earth, radio telescope on Earth that you see here, 500-meter diameter, is similar than the Galileo telescope to see through the universe. So that's not exactly what you need to make discovery in radio waves. What you need to do is have many more telescopes, maybe smaller, but separated and distributed on a large piece of ground around the Earth. So, and then the image resolutions come from the interferometry pattern that you have by combining the signal for the different telescope. So if you then populate your telescope on large area, like hundreds of kilometers, then you can resolve an image similarly as you would do with a large telescope that we use typically in astronomy in optical data. So that's the SKO project, the Square Kilometer Project Observatory, which planned to build 2 radio telescopes, so the largest infrastructure radio facility in the world, both in Austria, here with what we call rack antennas, or in South Africa with a dish antenna of 15 meters. In both places, we're going to develop a lot of these antennas, 130,000 in Western Australia and about 200 in South Africa. And those over tens of kilometers. And ultimately, we are thinking to develop that over thousands of kilometers. It's a global project. It involves countries all over the world. In the North America, lots of in Europe, in India, in China, and of course, in partner country in the south, where we have this radio frequency quiet zone where we can develop those antennas, so namely South Africa and Western Australia. We have joined this project as a Swiss partner. We started in 2016, we officially joined in 2022, and now we gather about 100 scientists all over the country here in Switzerland that are kind of distributed all over Switzerland in different universities, and of course we're using the CSS infrastructure to do our computation. So how much better is going to be this facility? Well, if you compare to what exists today, which are basically the rate sensitivity curves, depending on frequency or wavelengths if you want, we're going to be like 10 to 100 times, where maybe even thousands are more sensitive than current facility. So basically, what we're going to see with radio is something even better than what we are observing in optical data today. And that's, in a couple of years' time. So we're going to see more galaxies, more stars. Well, we're not going to see stars, but we're going to see galaxy and the gas distribution in the universe from very local to the very beginning of the universe. So we're going to see for the first time the universe in a global way. Of course, this is going to be a big challenge. Big challenge because this facility will produce humongous amount of data. And we are going to compress the data soon after the output of the telescope, because otherwise you can't do it, with correlation, with image making of your data, and I'll explain that later. And then we will deliver the data to a computing center where a user can use and play with the data. So let's just give you a quick idea how this is work. Interferometry, you have a signal coming from your object, from gas in the universe. Of course, they go to your telescope at different time, so you have to correlate the signal from the different telescope, basically making a Fourier transform of the sky. But of course, it's not just simple as that. It's more because in the universe you have many signals that are clustered together. You have different also effect in terms of the signal being pondered by the ionospheric or stratospheric effect or temperature fluctuation. So there's a lot of details you have to take into account. And of course, it's not like in this simple picture. You don't have like 2 telescopes, you have hundreds of them. So you have to do a correlation of all of these signals. So if you take this very simple, say you just have like 2, blob here, and you want to do Fourier transform, well, it's easy to do. But of course, it comes from image to what we call visibilities. But of course, when we do the observation with this radio telescope, because we have only antenna as a given place, we don't see the full signal of the visibilities. We just see that in partial term. So we also have to deconvolve the data, go from the dirty map to the real map. And to do that, we have to do a lot of computing. This is just a quick, numbers to see the challenge. And that's from recent data from LOFAR, which is an interferometry in Europe. It takes 6 days to image. To collect the data, to make the image of the data, but only 8 hours to acquire the data. So you see that you cannot sustain the flow of the data unless you make progress in the way you do your computing. And SKO, so the telescope we're going to build, will be like 3,000 more efficient in getting survey data. So we have also to be ready for this big impact. So that's also work we've been doing on trying to understand what are the complexity our processing of the data and where we can improve. And for example, on the left, we have a decomposition of all the computer power and where you put the effort in terms of the processing, and then we can analyze which of the element we can improve with the computing. So we've been working on an imaging system that is trying to improve that. I won't go into detail, but basically the idea here is to use a PCA separation of your signal from the bright to the dim sources and then do reconstruction at different levels. And then you can stack them together and then you basically have a better understanding of what you see in the sky. So this is a better algorithm, but of course you have to improve it. And so we were, thanks to PASC, to basically concentrate on this improvement, moving from just CPU simple calculation that people were used to do to go to GPU calculation, and that has a huge effect. And what's the application? Well, one of them is looking at the star, at the sun, or star, Nori-Bar star, which also have a strong impact on our satellite telecommunication, the space weather, and so monitoring the sun is something important on a daily basis. But of course, as an astronomer, you want to understand the universe. What you can use also this imaging technique is to really map the hydrogen in the universe from the very beginning, when you first form stars and galaxies from the hydrogen, and also map the universe as a whole, looking at all elements of hydrogen around galaxies and understanding the evolution of the universe. So observation is one thing. The other part is the simulation. Okay? Because if you want to understand your data, you need to simulate understanding the physical process that are behind. And that's the work that is done at the University of Zurich and University of Basel, where astronomers and computer scientists merge together and work on this SPH exact code. You have the physics that help you to do the understanding of the processes. You have gravity solver that helps you to put that into the context of the universe. The hydrodynamics, because you have gas also, you need to solve the gas equation. And you have also to partition all your data in an efficient way, otherwise, you're completely overwhelmed. Of course, you have also the computing topics about how you put that into your exascale computing, check it's scalable, checks it's well-balanced, checks the heterogeneity, the fault tolerance, and making sure that you have the energy to do your computing. This work, funded by PASC, was successful because the biggest computing allocation on LUMI was given to our team here, who wants to resolve the star formation and gravity in the turbulence region. And that's a simulation that I'm showing here. That was what was at the top of the type of simulation before, and now with SPH Exa, you can solve not only hydrodynamics, but gravity, and you can see how the structure in the star formation region is going to lead to star formation. So this data set that's going to come in a couple of years, 4 or 5 years, as a at the volume of 600 petabytes of data, we're going to have to deal with this amount of data. And so we are developing what we call a SKA regional center. This center will help, dealing with the data, distributing it to scientists. Scientists can then, make discoveries on the universe about these. And so we have all infrastructure to put in place, and that needs to be organized. We are going to do that in Switzerland with the Alps infrastructure. We are developing from basically next year what we call the SRCnet version 0.1, which basically can deal with about 10% of the data that will be ultimately produced, and to reach version 1 by 2030, when the full data set of the observatory will be coming. So this platform will enable data processing and visualization. We'll be able to run our computing program, analyze the pipeline, understanding the signal, make discoveries. So I will finish with here. Sorry for the issue of the font problem, but anyway, what I want to say here that we are making huge progress thanks to this new facility, the new way of computing. Without computing, we couldn't have done this, and there could not be no radio astronomy, just because a telescope is a radio telescope is a radio computing telescope. And we are very glad to work together with CSES and with the support of PASC to make this happen. Thank you.